Okay, well, I'm Neil Fraser from the Scottish Association for Marine Science, and I'm a researcher there in physical oceanography with a significant interest in the Atlantic Meridional Overturning Circulation, or AMOC. And I suppose I do agree that it is a bit of a clunky acronym, but we've had to sort of get used to it. I'm truly sorry that I couldn't be there in person. I really would have liked to join, particularly for the pub trip afterwards. But I think Oban to Aberdeen, I had a look at it and I just couldn't really find a convenient way to do that trip for the evening. But hopefully next time. So we've got this clunky acronym, the AMOC. What is it? Well, the Atlantic Meridional Overturning Circulation. It's a system of currents in the Atlantic whereby warm, salty water near the surface is transported northwards to the subpolar North Atlantic, the Nordic seas, and even the Arctic, where it loses heat to the atmosphere and becomes cold, salty water. And that combination of being both cold and salty makes these waters very dense. We get what's called North Atlantic deep water form, and it goes southwards again at depth. That's shown by this blue pipeline here in this kind of cartoon schematic in the middle. So I thought it might be worth breaking the acronym down a little bit. So what have we got? The first word is Atlantic. That's fairly self-explanatory. This happens in the Atlantic. But actually, I think it's worth stressing that this is unique to the Atlantic. There's no equivalent process occurring in the Pacific or Indian Oceans. Now, the second word, meridional, this just means north-south. It's a circulation happening, taking water in the north-south direction as opposed to east-west, like, along meridians, like the Greenwich Meridian, I suppose, is the origin of that word. And we can see on the right what effect this has on the global temperature distribution. This is showing the x-axis here is latitude, going from the South Pole up to the equator there, and then up to the North Pole. And the y-axis goes from 1,000 meters depth in the ocean up to the sea surface, and then up through the layers of the atmosphere. And we can see that all depths in the ocean and atmosphere system, we have the northern hemisphere is significantly warmer, up more than 3 degrees in some cases warmer than the equivalent latitude at the southern hemisphere, and that's due largely due to this AMOC circulation. And I think this is an important and subtle point, is that this circulation is not just redistributing heat from the equator towards the poles in a symmetrical fashion. It's driving heat from the southern hemisphere to the northern hemisphere and driving this hemispheric asymmetry. Overturning, again, perhaps fairly self-explanatory, but I thought this figure in the bottom left really shows it quite nicely. We've got the depth of the ocean here on the y-axis, and then the x-axis here is latitude, not covering quite such a large range this time. And we can think of it, we're looking kind of side on into the ocean from the perspective of maybe Europe or Africa here. And what we're seeing here, these black contours, are the streamlines. These are the lines that the ocean circulation flows along. And we can see that we're flowing northwards towards the surface, and then it's going down when we get to these subpolar latitudes, and then back again. So it's this concept of overturning, really. You can think of it as, the system's often described as like a conveyor belt. You can, like a sort of conveyor belt or a sort of treadmill type pattern. And then I think circulation, that is self-explanatory. It's just the circulation of the fluid. So a couple of facts I just thought were interesting to emphasize how big and important this is. The AMOC carries around 20 million cubic meters of water per second. That's around 100 times the discharge of the Amazon River. So big that we don't use the unit cubic meter per second. We call it 20 spheredrops, which is a sort of shorthand unit we use in oceanography. after a sort of pioneering Norwegian oceanographer called Harald Sverdrup. So you'll see the unit Sverdrup used quite a lot in this presentation. And the heat delivery around the subtropical latitudes where it's highest, the northwards heat delivery in the AMOC is about 1.25 petawatts, about around 60 times global human energy consumption. So moving on to some of the dynamics of the AMOC, what makes it so interesting? So it's a bistable system, and that means that given one set of external forcing, the system can exist in two stable regimes. This was first shown by Henry Stommel in a seminal paper in 1961, where he really, this is often referred to as the Stommel box model. He really boiled down the whole Atlantic system to a kind of North Atlantic and South Atlantic box, each with different densities. And the circulation, we have a shallow circulation and a deep return flow, which is driven by the density difference between the two boxes. And this is exactly how the AMOC works. It's driven by the density difference between the South Atlantic and the North Atlantic. Now, the density in each of these boxes is controlled by both the temperature and the salinity. That's why we call this thermohaline circulation. It's both got a thermal component and a haline, a salt-driven component. And these both affect density in different ways. And the regime we're in now, that's the strong AMOC regime, is a regime where the density is dominated by temperature. However, if we add more fresh water to the system and change the conditions, we can go into a different regime where the density is driven primarily by salinity, or the freshwater content of the ocean, and well, yeah, that's a sort of that corresponds to the kind of weak AMOC regime that can occur, or even a actually change direction of the circulation. This was shown more recently in a simulation by Ed Hawkins, where they took this is with a slightly more advanced computer simulation, and to try and explain this, they took a simulation of the Atlantic, and they increased the freshwater forcing into the North Atlantic. That's the fresh water being injected into the North Atlantic. You can think of this as from precipitation, from melt off of Greenland, from rivers, and fresh water exported out of the Arctic due to sea ice melt in the summer. So if we start here at 0 on the red curve here, we have, sorry, the y-axis is the strength of the AMOC. And as we increase the freshwater forcing, we see that the AMOC is pretty stable. It doesn't react much until we hit this critical threshold where the AMOC strength drops dramatically and the circulation completely collapses. And this is the system transitioning from this thermal water-driven regime. We've hit a threshold where it's switched, and then as we continue along the red line, increasing the freshwater forcing, we see that the system stays weak. And then what happens if we then turn the freshwater forcing back down, moving back the other way on the blue curve now? If we turn the freshwater forcing down, we might expect to hit the same threshold and the system flips back again. In fact, that's not what happens. We have to reduce the freshwater forcing to 0 or even become negative. That is, we are extracting fresh water from the North Atlantic before the system reverts back to this on state, or this strong AMOC state. So this is an example of hysteresis, where whereby the system has a memory, and it goes to show that if we hit one of these tipping points, if the system suddenly collapses, that might happen relatively easily. Getting it to switch back on again can be very, very difficult. So this is a big concern, that the AMOC might be approaching one of these tipping points induced by fresh water in particular. This idea of switching from a thermally driven regime to a to a haline, to a salt-driven regime. And this was shown again in a very recent paper by Van Westen et al. This is in a much more state-of-the-art Earth system simulation, which they ran for 2,000 years, and they forced the North Atlantic with a lot of fresh water. I think it was actually a bit of an unrealistically high amount of fresh water, but it was to demonstrate that this behavior is possible in these fully coupled Earth system models. And the strength of the AMOC there was fairly stable. And again, we see this tipping point occur after around 1700 years. And what we're very worried about, I suppose, and what's been particularly, grabbing the headlines recently is, we want to know if we're currently in this sort of situation here, where the AMOC is weakening and approaching this sudden collapse, and is there still time to do anything about it? So we want to know what the AMOC has been doing over the last 100 years or so, since the onset of the industrial era, to try and see, does the pattern match with approaching one of these tipping points? That's certainly one of the important questions we want to answer. And so there's been a lot of research looking at paleoproxy records around the Atlantic region to try to reconstruct sort of century scale AMOC variability. So these proxies are, not direct observations of the circulation, but they are something which is thought to closely correlate with the AMOC. So there's a whole set of time series here based on ocean temperature, from coral records, from sediment cores, from Greenland ice cores, and they've all attempted to reconstruct past AMOC behavior from these proxy records. And there's a fairly many of the proxies suggest that the AMOC has weakened over the last 100 years. There's a little bit of disagreement in exactly what that pattern of variability looks like.
What's happened, Neil? You've gone quiet.
I've gone quiet. Okay. Can you hear me now?
Yes.
Let me, it says it can't.
You just went quiet.
Okay.
Did you go out and then come back in again? No, you're still co-host.
Hi, can you hear me?
Yeah.
I'm sorry about that. Sorry?
You're in twice now.
Oh, the other me should leave. Sorry, let me try and get that set up again. It for some reason asked me to restart my browser. Okay, sorry about that. Let me present. And then share. Okay, can you see my slides?
Yep, looking good.
Great. Okay, so I think I'd covered what I wanted to say about this. We have these paleoproxy records which tend to suggest that the AMOC has weakened since the onset of the industrial era, but there's a bit of a disagreement into how representative are these records of the AMOC versus other climate signatures. If we look in the latest generation of climate simulations, as the CMIP6 models, they give us a slightly different picture of what's happened over the last 100 or so years. So since 1850, this panel on the left shows the the historical AMOC behavior in a whole range of different CMIP models, climate models, up till roughly the present day. We can see there's a huge range in the strength of the AMOC in these different simulations, and also in the patterns of variability that we see. The thick black line shows the multi-model mean, and that in fact doesn't suggest a weakening over the last century or so. There's a slight strengthening, although it's not really significant. Where the models do agree fairly unanimously is that over the coming century we will see significant AMOC decline, and this is shown in these panels. The different models here are shown in different panels here. It doesn't always have the same gradient, it's not always the same magnitude, but there's a pretty unanimous result across these climate models that the AMOC will decline over the course of this century. And the paper that came out just last week by Sibrin Drifthow, which was picked up in a few news outlets I saw, was taking the simulations which ran all the way out to the year 2500 and looking at this AMOC, not only the AMOC decline but the behavior afterwards. And I think very interestingly, we see that over the first half of this century, we see AMOC decline in these three different colors, which are the different emission scenarios. The blue is the low emissions, then intermediate, and then high emission scenarios. We see that regardless of the emission scenario, we see AMOC weakening over the next 50 or so years. So in a sense, that the models are just suggesting that's already locked in. But where we see a big spread is in the subsequent recovery. The blue low emission scenarios see a recovery over the following century back to near pre-millennium values, whereas the high emission scenario, it switches off and stays off. So we might be kind of, I suppose what these models are suggesting is that we can expect some AMOC decline regardless of what we do within our lifetimes, but it's what happens after that where we still have some control over that. And I want to talk now about something which is very, I've been talking so far about things I don't know much about. Something I do know about is making direct observations of the AMOC. So there's several transatlantic observational arrays which monitor directly the strength of the AMOC. And I'm going to pick two of these out right now. First of all, the RAPID array in the subtropical North Atlantic has been running since 2004. And the time series from RAPID is shown here. It's the blue line here in this bottom right panel. So this is the 20-year time series of AMOC at RAPID. Now, 20 years it's perhaps not that long when we're trying to resolve climate scale variability, because we have a lot of interannual and multi-annual noise above which we have to pick out these anthropogenic signals. And RAPID at 20 years, there is a slight negative trend, and it's just starting to perhaps rear its head to become a statistically significant trend that we can actually resolve any AMOC weakening with the RAPID array. And then the OSNAP array in the subpolar North Atlantic, this is the one that we at SAMS are heavily involved with. This observes the AMOC right adjacent to these convection regions. So we're right next to the regions where this dense water is formed. And this has been running since 2014, so only 10 years, and it gives us this time series here. The black line is the full overturning stream function, the full AMOC strength at OSNAP. Again, there's no significant trend. This is the 8-year time series at OSNAP. There's no significant trend, but we are starting to pick out climate signals which have been we're starting to pick out signals which have been related to climate variability. So it's a long waiting game making these observations. We do need simulations and proxy reconstructions as well to provide context. But these simulations are extremely important for kind of benchmarking and validating the simulations which we rely on for projections. And the rapid and OSNAP observations have become, a sort of a key benchmark for climate simulations to compare against. We want to use the simulations which can represent the present day accurately. We trust those best to tell us about the future. And a little bit more about what we do at SAMS, just to finish, is that we run this program called the ELIT Array, and this is a row of moorings which occupies roughly the easternmost third of the OSNAP array. So these yellow points show hydrographic moorings which have been in place continuously for 10 years. And an example of some of the data that we get back from them is shown here. So this is from these moorings in the Rockall Trough here. We have 10 years of salinity. This is salinity as a function of depth and time. We can see that at the start of the record 10 years ago, the conditions, it was fairly salty. It then got very, very fresh. And it's not until just last year, really, that we saw the conditions return back to, or even exceed, the levels of salinity that we saw at the start of the record. So yeah, there's a lot of decadal scale variability in the conditions in the North Atlantic, and particularly there was this fresh blob circulating around over the last decade. And we also, at the eastern boundary, there is a boundary current which follows up at the continental shelf break here. And we observe that continuously using subsurface autonomous robots called sea gliders. And we have sea gliders out there continuously. And over the last 5 years, we've taken coming on for 300 transects of the slope current, measuring its temperature, salinity, and the velocity. And this color scale shows the velocity here. So we have red northward flow over the upper slope here, and then we have this counter current at depth, which was something that wasn't known about until this sea glider survey, and this actually acts to weaken the AMOC slightly, because it's negative southward flow, where otherwise the flow is mostly northwards. So I suppose that I just wanted to give a little bit of a flavor of, in practice, how are we actually doing this? These arrays are very expensive, and they're very labor intensive, with a lot of specialists having to spend a lot of time at sea to make these observations happen. But I think trying to argue the point, because I think they are very valuable for the whole of the climate science community. Here's a nice shot of SAMS and the marina in the background with some of our sea gliders looking fancy. So I can end there. I've just got some references, but other than that, I'm happy to end there and take some questions, or take questions at the end. Thank you.
Thank you very much, Simon. Neil, sorry.